continue worksheet 16b, and after we find out the internal forces and on segment ABD with all the direction as shown, and we have 5 different loads: Fx, Fy, Mx, My, and Mz. And then we will apply the superposition and consider one at a time. So let's do that here with a stresses step that we need to do. Find out stresses and consider one at a time. So in this case, the first, let's go with the Fx. So the first one, we have stress due to Fx. Stress due to Fx, and Fx in that case equal to 320 pounds. So what is that Fx? As you can see on ABD, Fx is the normal internal normal force go out of the cut, so it creates both point A and B normal stress in tension. So you can see that R, A, and B, we have the normal stress, and in this case the Fx go through X, so it will be normal stress is sigma x equal to P over A. So in that case you can see Fx over area, and Fx equal to 325 divided by A, so pi, the radius diameter is 4 inches here, so the radius will be 2 inches. So that here 2 inch square. So from that we can have 80 psi, and it will be in tension on both point A and point B. So from that, how can we draw the 2D stress block for each of them? So we have A, and we have B. So point A here, B. So that you can see for B, for A, it A, the plane A there, the horizontal plane here, that is the G plane, and the plane vertical plane is the X plane. So in that case, as you can see, it's better to draw that in X and Z plane. So here you have X plane and Z plane, and similarly for B, you can see that the plane, this plane, horizontal plane, now become a X plane because perpendicular to X axis, and the plane along the longitudinal axis is perpendicular to Y, so Y plane. So from that we better to draw that in X plane and Y plane, and I just use similar to the orientation that we have. So it will be X, and it will be Y. So here, only sigma x in the first force, so we have sigma x tension, so that one follow the x 80 psi, and tension should go up the cut. Similar for B, I can have that also 80 psi. The other also 80 psi. So that's the first load due to Fx. The next one, we can have stress due to Fy. And Fy we have here equal to 165. And in the negative y axis. So 165. 65 pound. Positive y axis. So let me draw how it look like so that we can be able to see in 2D. You see this cross section of the shaft, and x is the perpendicular to the page and go out of the page. The z axis basically go up, that's z, and the y-axis go to that, and point B here, that is B, and you see A. So cross section in AB, as you can see there, and X is perpendicular to that surface. So the Fy, you see Fy 165. So that the Fy, as you can see on the cut, on the plane of the cut, on the cross section. So it will create the shear, transverse shear force. Good. Okay, and as we already know, for the transverse shear force, tau equal to VQ over IT, and it will be maximum at the neutral surface and neutral axis, and then 0 at the outermost fiber. With that force direction, as you can see here, point A on the outermost fiber compared to the force Fy applied. So at point A here, the tau equals 0. B go to the neutral axis of the force with that direction, so it will be maximum. So as you can see now, it creates the stress at shear stress, but at A, the tau x tau in that case, as you can see, it follow y direction on the x, so tau xy equal to 0. Now at B, point B, maximum. So we have tau for B, it will be also tau xy, because that is on the x plane and follow y direction. So you have tau xy equal to, and if you see at point B, it will be a negative tau. So you can see that it's negative, right? Because it's opposite of y direction. And the question is VQ over IT. So let's put V, put negative later when we plug the number in, VQ over IT. And for, if you go to the inside cover of your book, we have the if we have a cross section like that, let's put here cross section, and the neutral axis, it's in neutral axis. And what we have, the Q is the first moment of outward area. So basically that one for point B, this is point B, and you can see there. So that in neutral axis, and then it will be equation, if you recall, Q NA equal to, and you see only one area, so we have one A apostrophe outward areas. And in this case, the A bar is from the neutral axis to the centroid of the green line here. And if you follow the inside cover of the book that we do it in transverse shear stress, that distance here is y bar, and that equal to 4 over 3 pi. So from that we can plug in here with the tau xy equal to vq over it. So that it equal to v, so it will be fy q, so y bar times a apostrophe, y bar is 4 over 3 pi. Area of our what area, so you see half of the circle, so you have it pi r square over 2, because that is half of the circle. And then we go to the area moment of inertia for circle, pi over 2, pi over 4 r square, that is I, r4 for the area moment of inertia. And then we have the t, the thickness at the point of interest. The thickness here of point B is basically that is t, the whole area, as the whole diameter, that is 2r, as you can see there. So we have that here, it will be 2r. So we plug on of the number in, we have tau xy for point B equal to fy is the opposite of y, so we have 165, then negative, and then 4 times 2 over 3 pi 2 square over 2. Our what areas, 5 over 4 times 2 power 4, 2 times 2. From that we get this one equal to 53.3 KSI. And pounds, as you can see, the answer is pound, and then we change it to negative, change it to KSI. We have that number. So from that one we can go ahead to find out draw the state of stress for stress due to Fy. So we have A and B again. So you have similarly in here you have X, Z, and then X and Y for B. So they have point A and point B. Point A, nothing. Yeah, no stress at A. Point B, maximum negative 53.3. So at where the positive x-axis is on the right, as you can show here, and that is negative 53.3 is mean opposite to y direction, so it will be go up. My positive y going down, so that one it go here.